In section 1.1, we briefly went over the concept of a field, and we talked about two different types, scalar and vector fields. And even though in the textbook, vector fields section 1.5 only takes up maybe a page, it's a concept that can really throw you for a loop. So a vector field is a field in which its value at a given point changes magnitude and direction as you move along the region. So we used this graphic before for a vector field, and as you can see, as you move downward and sideways, you can see that not only do the magnitude or the lengths of the arrows change, but also the directions that they're pointing. And with vector fields, the value of the function which governs the region, so say the square region or a field, if you want to find a value from that function, it has to be determined from the coordinates of a point in question. So that means if I tell you what's the value at 0, 3, 1, then you gotta use 0, 3, and 1, so x is equal to 0, y is equal to 3, z is equal to 1, in your function to be able to find the value. So to be able to actually represent this vector field, which we're going to generalize as g, as a function of some position vector r, we write it as g of r, just like with functions in algebra, like f of x. And like I said, r, from previous lectures, we learned that r is a position vector. And this works great. You know, you're trying to find a position vector and everything like that, but what about other types of vectors? Pulling directly from the book, this is straight out of your book, we're going to assume that we wish to model a certain portion of the ocean for water velocity. And we're going to assume that it's going to be near enough to the surface. To be able to actually start making our model, the first thing we have to do is establishing our coordinate system. And we're going to use a right-handed coordinate system just because it makes our life easy, and it's what we've been doing. So we're going to keep it in rectangular, and we're going to have z pointing upward from the surface of the water, x is going to be pointing north, and y is going to be pointing west. And the origin of our coordinate system, so essentially z equal to 0, is going to be at the surface of the water. And since z is pointing upward, that means as we go further into the ocean, z is going to become more and more negative. Now we actually need to get an equation that will govern our region. To be able to do this, we need to understand that our velocity vector v at any given point is going to be a combination of all the velocities in the x, y, and z direction. Using component form, which we learned in a previous lecture, you can actually write this as v is equal to v of x, a hat x, plus vy, a hat y, plus vz, a hat z. Using v as our governing equation for our region, we now can write the velocity at every given position vector as the following. Now, just a word of caution. If you're reading this directly from the book, it is very easy to think that what they are doing is multiplying the position vector by the velocity component. So like saying vx times r. That's incorrect. It's actually saying that v is a function of r is equal to vx of r. So vx is also a function of r, a hat x. And the same thing for vy and vz. And this is because if you remember back in Calculus 3, linear algebra, and some physics courses, each of those components, vx, vy, vz, can actually be a function of the position. So for example, we could have a vx component that's governed by x squared plus y over 2. It actually becomes a function of the position rather than just multiplying it. So to be able to actually see what's going on with this field and to be able to see how we use fields, we're going to make some assumptions for our model. And once again, this comes directly from the book. So first, we're going to assume that we're going to look at a portion of the ocean wherein all of the water is moving purely northward. And one good example of that is a section of the Gulf Stream on the east coast. It all moves northward. So since everything is only moving in north or the x direction, we know that there's no y component and no z component to the velocity. So this means vy and vz are now equal to 0. We're going to further assume that the velocity changes very, very little, almost none, in the x and y directions and is only constrained by the depth. So what this means is that if you were floating in the ocean or if you had scuba gear and you were neutrally buoyant at a certain depth, if you were to move yourself left or right or even just drift forward, your velocity is going to remain constant so long as you remain at the same depth. So what this all means is that for our model is we're looking at a chunk of water where all the velocity is moving north and the velocity is dependent on the depth only. Once again, pulling straight from the book, they have an example expression for our vector field given as v is equal to 2e to the z over 100 a hat x. And the a hat x comes from the fact that x is the northward direction, and we only have a northward component. So what's interesting is let's actually start plugging in values for our position vector. So first we're going to look at the surface of the water. Now, I've written down that we have a position vector equal to 0. This is kind of right, kind of incorrect, but I make an assumption that we know that the velocity, so the v equation, has no dependence on x and y. So I don't really care about the x and y positions in the position vector. I only care about the z. So at the surface, where z is equal to 0, we're going to have r is equal to 0 a hat z. And if you plug in the z value, you're going to get a velocity of 2 meters per second, which is very easy to see. You could do it on your own in about 5 seconds. But what if we change our depth to 100 meters? So now z is equal to negative 100. Our position vector now is going to be some arbitrary x value, some arbitrary y value, which once again we don't care about because the governing equation has no dependence on x and y. If we plug in this negative 100 to our equation, we're actually going to get a velocity of 0.736 meters per second. So one of the interesting things about this field, and something that's just a takeaway for the rest of this lecture, is that as we continue to go deeper and deeper and deeper, our velocity is going to continue to decrease. However, as we go deeper or even go up in the water, we're going to remain flowing in the same direction. So regardless of how deep you go and how fast you're going, so how big your magnitude is, it's going to be pointing in the same direction.